Okay, so today we will talk about section 11.6. Section 11.6, directional derivatives and the gradient vectors. And so first of all, let's recall the material in section 11.3. Section 11.3. We talk about the partial derivative. Partial derivative of f, which is with respect to the derivative, the variable x, then and with respect to the variable y, we have the two definition. We have these two definitions. And actually, for the partial derivative, it's just the special case of directional derivative. It's just the special case, but it also plays an important role in directional derivatives. And later I will tell you why could I say that. Okay, so in section 11.3 we talk about partial derivative and what does it mean in the graph. Of course, for its partial derivative, if we consider the variable is x, differentiate with respect to variable x, then we fix the constant y. We let y be y0. So we fix a constant. So here we have a function g here. The graph, it's the graph g equals f of x, y. It's the graph of the function f. It's the graph of the function f. And we can see the point x0, y0, and it's in xy plane, so the g value equals 0. And once we plug in the value x0, y0 in the function in this function f, then it's over here. So for this point, its coordinate is x0, y0, g0. I mean f of x0, y0. For its g value is this one. Okay, and what's the partial derivative with respect to x? It means that we fix the plane y equals y0. Here is y, here is x0, here is y0, here is y0. So we fix the plane y equals y0. So for the graph and the plane y equals y0, we have the intersection, and I use the red pen. It's our intersection. Here, it's our intersection. And for the intersection, for each point in the intersection, its y coordinate is always y0. For each point, its y coordinate is always y0. It's always y0. This one. For each point in this line, its y coordinate value is always y0. Okay, so you could view it as one variable, just have the variable x. So we consider its derivative, and we denote by f sub x, this one. So in this case, it's one variable, so its derivative means that it's the slope of the tangent line in this point. In this point, we have a tangent line, and it's the slope. We define it by this way. Okay, so if we say this one, then we have the direction. We have the plane y equals y0. So you could view it this way. We could consider, okay. And how about f sub y? If we consider partial derivative with respect to the variable y, then we fix the plane x equals x0. And its definition becomes here. So s is a constant. So now we consider the constant s equals s0, and what does it mean in the graph? We have the plane s equals s0, and then the plane g equals f of sy. So they have the intersection. The intersection in black color. The intersection. And then in this intersection, each point is s coordinate value is always s0. So it has a form. So you could view it as you could view it as the function whose contains just single variable y, and g depends on, of course, g depends on the y. So we consider we differentiate this function with respect to the variable y. Okay, and so f sub y means that the tangent line, the slope of its tangent line, So you can see just y coordinate, we have the change. We do some change. And here, just x coordinate, we have some change. Okay, and then now we consider general case. But for general case, yeah, later I will tell you. Actually, it's why I say it's just special case. But I think in the graph you have you could see that here we consider two planes. One plane is y equals y0, another plane is x equals x0, right? So you could view it this way. We consider another general plane. And then for this general plane, we should, if we start from this point, P, S0, Y0, 0, we should have a direction. And once we have the direction, we could decide its plane. So for this direction, if I call it AB, U equals AB, you see, because here we just focus on SY plane. So we just consider it's a vector in R2 space. So we just consider a vector in R2 space. Okay, so first of all, I would like to tell you the directional derivative of f at this point in the direction u. I want to tell you the definition, but I want to explain it by the graph first of all. Okay, so first of all, we have a vector. It's a vector in R2 space. U, and of course we have a function f of g equals f of it. We have a function which contains two variables, f of x, y. And we consider its graph. Its graph is this one, g equals f of x, y. I graph it in blue color. G equals f of x, y. Now, and we fix one point P, S0, Y0, 0 is over here. And so it has a corresponding value here. I mean this point is, for this point, of course it's exactly S0, Y0, its g value equals f of x0, y0. This one. So this point is this one. For the point over here is this one. Okay, so now what's the directional derivative? You should fix one direction. So now I'm giving you the direction. I give you a direction vector. A direction vector u. U is a vector in R2 space. And we have two components A and B. And I give you the unit vector. It's the definition. I give you the unit vector. Unit vector means that its length is 1. And if I denote it by this one, AB, you could view it this way. It's A0 plus G0, 0B, right? And so for the scalar A, we could take out. So for the scalar B, we could take out. So for this vector U, AB, we have the vector. Originally, I don't know this part, probably, if I denote it by this one. Here, this one is our vector U, and its length is 1. It's a unit vector, so its length is 1. And I want to know its component, the component mean. And we could write it this way, it's this one. A times 1, 0 plus B times 0, 1. So indeed, this part is A, the length is A, the length is B, the length is A, the length is B, and the length is 1. Okay, so if I denote it by this one, I mean the unit vector AB, then the scalar A means this part, it's the length. The scalar B means its length, Okay, so now we decide one direction vector. And in this direction vector, and we fix the point P. Xg is in the xy plane. P, S0, Y0, G value equals 0 is over here. And we decide the direction. And in this direction, we consider the plane. I mean, in this direction we let g be any value. In this direction we could design a plane, and I just grab it in green color here. For this green color, we have the plane. So in this plane, each of the plane comes from this direction. We have a direction, and the direction is this one, AB, this one. Okay, so in this direction, yeah. Now we can see 2 points, but we can see 2 points because we want to define its definition, define its directional derivative. So we should have 2 points, and for derivative. Okay, for derivative, originally we define it by this way: limit delta s approach 0, delta y over delta s. This form. Change in y over change in s, and let change in s approach 0, right? So now we start from this part, change in x. So change in s, we should have 2 points. So the first point is we start from this point. We consider this point is derivative, so we start from this point, and we choose another point. It's over here, q. It's over here. We choose it, and the change is h. If we denote the change by h, what's the length? What's the length? In this direction, as we say, if the length is 1, then x component is a, y component is b, right? But now the length is h, so this component should be a times h. This component should be b times h, right? So what's the coordinate position? Here is x0, so you should pass h. Here is y0, y coordinate is y0, but you should pass bh. Here is our x, y, g. Don't forget x, y, g. So for x coordinate we pass h. For y coordinate we pass bh. And the length is h. The distance, changing x, the length in x, the length in h, sorry, the length in h. Okay, and so for this point, it has the corresponding value. G value, and we consider their difference. I mean, G value, their difference. So here you could see the difference. Divide by the change in this direction. I mean the length h. Okay. And finally, let h approach 0. Just we choose these 2 points, and we consider the line. But you could see that there are some errors. So of course you should let h approach 0. Okay. Yeah. So it's called directional derivative of f at the point x0, y0 in the direction u. Okay. And actually in this case, you could see that if I choose the unit vector u, if the unit vector u is this one. Let me see. Unit vector u is what's it? If the unit vector u, if you see, it's something like for this unit vector, we can see the plane. But if the plane comes from the unit vector u is this one, 1, 0. It means that we consider this direction. Actually, we just consider this direction. So this direction. So in its definition, it means that we just consider the vector 1, 0, right? 1, 0. So just the case 1, 0. If the unit vector we choose is 1, 0. So in its definition, a is 1, b is 0. So here is y0. Here is s0 plus h. Here is x0, and it's exactly the partial derivative with respect to x. Right? And if so, it's just so what do we have? What do we have? It's our node, the first node. The first node we have is let me see. We know that first one, if u equals 1, 0, then du f of s0, y0 is exactly f sub x s0, y0. It's exactly this part, right? This part. And the second one, if we choose the unit vector u by 0, 1, then it's directional derivative. Now it's 0, 1, so it's 0, 1. So in x coordinate we don't have any change. So it's but in y coordinate is y0 plus h y0. So it's exactly this one. So if it's this one, then okay, right here. So second, so it's if u is 1, 0, 0, 1. If u is 0, 1. Then du f of s0, y0 it becomes y s0, y0. So it's so for partial derivative is just the special case. Partial derivative is just the special case for the directional derivative. But it also plays an important role because when we want to consider directional derivative, if we use the definition, it's complicated to solve it. So we will use the main result. It's very important main result. We all just use that. Yeah, and for its proof, we should use some chain rule. So for its proof, if you are interested, you could check in the textbook. Yeah. So for that part, we just give you. You just need to know how to use it. And we still have one name. We still have another name. I mean, gradient vector. So for gradient vector, it's defined by this way. When we consider partial derivative in x or partial derivative in y, partial derivative in x or partial derivative in y, and plug in the point x0, y0, then for this vector s sub x s0, y0, f sub y s0, y0, for this vector, it's a value, so it becomes a vector in R2. For this vector, we call it gradient vector of f at this point. We call it gradient vector. Sometimes vector we just skip it. Okay, and then it plays an important role for gradient vector. Gradient vector directional derivative is very important topic in chapter 6. In chapter 11, gradient vector. And what does it mean in the graph? Here I could tell you directly to tell you its meaning. If we say we have a function g equals f of xy, it's our function g equals f of xy. Here let me tell you gradient vector, what it means. We have function g equals f of xy. We have a point x0, y0. What does it mean in the graph? Gradient. It means that for this function, once we plug in the value x0, y0, we have fx0, y0. We must have it's a number it's a real number, and it means the height, right? Here we plug in x0, y0, we have the point, and then for the point f of x0, y0, if we denote it by k, for this point, its x coordinate is x0, y coordinate is y0, z coordinate is the value f of x0, y0. And for this value, if we denote it by k, now we consider the function whose height is k. I mean, we consider f of xy equals k. It's like the label curve. Just it means the label. It's related to the label curve. Here we consider the height for the function, if its height is k, k is the number, then there are some point x1 here. Here I circle it in black color. It means that all the point, its height is k. All the point, its g value is k. All the point in the circle, its g value is k. It has a height k. It has height k, or you could say its g value equals k. Then we consider its projection. Okay, projection to xy plane. So when we consider its projection to xy plane, we have this one. Probably it's this one. So it's just the label curve, right? The label curve. So for the label curve, it's this one. So in this label curve, it satisfies this equation, right? Fsy equals k. And in this label curve, of course, it passes through this point, P, S0, Y0, 0. And now, what does gradient mean? Gradient means that for this point, we have a curve, and we have a point, and this point passes through this curve. So we could consider its tangent line. And once we have tangent line, of course, we have the second line. So normal line. Sorry, I correct tangent second. No, it's normal line, which is orthogonal to tangent line, right? We have a normal line. So for its normal line, normal vector. For its gradient, for the direction of gradient vector, it's exactly in this direction. It's a normal vector for the tangent line. It's the normal vector for the tangent line. So for this direction, it's our gradient. Okay. So it means this one. And for this part, we will say more in this chapter, second topic. This chapter. So now this section, it contains two topics, and it's second topic is they are related. Anyway, so gradient vector, it means this one. It means we consider the function is gradient vector at some point s0, y0, then you should plug in the value s0, y0, then you could get f of s0, y0, you could get the constant. It's constant. And now we fix the constant. Let f of sy be the constant k. Then we have probably we have a curve, and then we consider its projection, and its projection is over here, and then in its projection, of course, it passes through this point P, s0, y0, 0, and so it has a tangent line, and of course, it has a normal line. So for its gradient vector is in the normal line. It has the same direction as normal line. Yeah. Okay, now I tell you the main result for the directional derivative. It's related to gradient. Gradient is related to partial derivative, right? So for directional derivative, actually we will calculate directional derivative by gradient. So both of them are important. Yeah, so I will tell you the main result and give you one or two more property, and then we will check some example. Yeah, in this section, of course, you should just check the example. It will be not very difficult one. Yeah. Okay, so for this part, is very easy. So for your notes, partial derivative is just some special case. So for this part, here I just keep it again, and erase it later. Okay, so for our note, for the note, as we said, the directional derivative. It's called directional derivative, but it's something like when in chapter 2, when we say derivative, we also have another name. It means the same thing, right? So it's also the rate of change. Rate of change of f. Rate of change of f at s0, y0 in the direction u. In the direction u. In the direction direction u, in direction of u. And the third one, it's the most important thing you should memorize. It's the most important thing you should memorize. Just memorize this for this result. It's a theory. Okay, actually, let me see. Yeah, probably I could just say give you these two notes, and for this one, just knowing by a theory, because it's the most important thing. We have the theory. We have a unit vector u, a, b. It's a unit vector. And for our formula is du f of s0, y0. Our result is that it's the gradient f of s0, y0. And the u. For the gradient, as we say in the definition, it's a vector in R2 space, right? And what does it mean? It means that, as we say in the graph, we have a we plug in the value, the value s0, y0, we have the height f of s0, y0, and we have a curve. And for each point in this curve, they have the height k, they have the height, the same height. And I consider its projection, so we have a label curve here. It's our label curve. It's satisfied f of sy equals k. And then the k is this one, k is this one. So this point P is over here. And what does gradient mean? It means that for this curve, we have a tangent line, and so we also have a normal line. We have a normal line, and the gradient is in its normal line. It's in its normal line. So it has the same direction as its normal line. Okay. Yeah. So here is our gradient, and now in this example we use the unit vector u is this direction u. So now we have two vector. Here is our u is this direction. So u is this direction. U is this direction. Here u is this direction. Right? So we have two vector, and the directional derivative is exactly these two vector their inner product. So it's very nice result. Otherwise, if you check it, compute it by definition, it's complicated. But now, for any problem, if you want to consider directional derivative, you just need to check its gradient, and consider their inner product. Then we are done, right? So it's very important result. It's very nice result. And then now, for the two vectors, their inner product, we also have a result. Here we have a vector A, we have a vector B. And their inner product, what can we say? If we have a angle theta, we have this result, right? Cosine theta equals AB, their inner product, divided by their length. Right? And in other words, it means that their inner product equals, we multiply by denominator 10, so it's length, product of their length times cosine theta, product of length times cosine theta, this one. So it becomes gradient f s0 y0 is length times u, unit vector u is length times cosine theta. Theta means their angle, the angle between them. So in this example, is our u, is our gradient f s0 y0. This one. But u is unit vector, so it's equal to 1. It's equal to 1. This one. And then now, so for the directional derivative, originally we have, the most important result is this one. But for this result, we could say more. Here we have this one, and what does theta mean? Theta is the angle between u and the gradient f s0 y0. Unit vector. And the second part, in particular, we could say more. In particular, since it's equal to gradient is length, gradient vector is length times cosine theta, then we could say more. What's the maximum of directional derivative? Maximum. And what's the minimum? And it occurs, I write down the result. First one, maximum, then maximum. So for its directional derivative, originally for the unit vector, we don't know its unit vector is exactly unit vector. We just know that it's unit vector. Its length is 1. We just know its length is 1. We don't know the value a and b. And we have this result. But in this result, you could see that for this result, gradient f this term is independent on u. It's independent on the unit vector, right? If we have a function f, and we could consider its gradient directly, and plug in the value s0, y0. So for this term, it's independent on u. So we could check it directly, right? And then now we want to know for its directional derivative, for any unit vector u, its directional derivative is maximum. Then just in the case when cosine theta equals 1. When cosine theta equals 1, this part is 1 times this guy. So of course it's the maximum. Gradient f s0, y0. And it happens in the case when cosine theta equals 1. And when cosine theta equals 1, cosine is a function. So cosine theta equals 1 is exactly when theta equals 0, right? So cosine theta equals 1 means that it has the same direction. The direction u we choose. The direction u we choose is exactly in its gradient direction. So gradient f s0, y0, the same direction. And the minimum, it happens in the case when cosine theta equals -1. Then it becomes negative length of gradient f s0, y0. This one, it's the minimum. And it's the minimum, and it has the direction when cosine theta equals -1, and cosine theta equals -1, it's pi. So it's the totally different direction. So here is our gradient. Here, so cosine theta equals -1. So in this case, theta equals pi. Pi means 180 degree. 180 degree. So it becomes negative gradient f as 0, y 0. Converse direction. Converse direction. Okay.